So hello and welcome to my talk on relational test tables. These are a table-shaped specification language for reactive systems and relational properties on them. The table-based notion is derived from concrete test tables which are used in industry today. So with relational test tables, we are targeting the practicals, the engineers. This work was originally accepted and presented on the Formalize last week. And to get into these topics, I want to start with a simple form of relational specification. Let us consider relational specification for pure functions. So here Q and P are functions which maps their input values to an output value. So on the left, I sketch a proof obligation as a Hall triple. Phi is the relational precondition which describes the relation between the input values of P and Q. And in contrast, psi is the relational postcondition, which describes the relation after the execution, the invocation of P and Q of the output values. So to make this more concrete, if phi and psi states the equality of the input and the equality of the output, this proof obligation would state the program equivalence. So for pure functions, this is very easy. But for reactive systems, the game is very different. Reactive systems are very common in cyber-physical world, for example, in automotive production systems or in the automotive domain. So their characterization is that these systems are triggered periodically to react on the current situation of their environment. This means that the system runs forever, like an unbounded loop represented on the left. So in each of its execution cycles, it reads the sensor values from its environment, executes the internal logic, here denoted as P and Q, and computes the actuator values which are written on the bus system, for example, and then the system waits for the next cycle. So this means first, the program is run forever, and also P and Q are allowed to maintain an internal state. So now, if you want to compress the relation between reactive systems depicted on the right, we would make it on each cycle because they are not terminating, there's no end. So in each cycle, we would state, okay, for this particular cycle, there is the relational precondition and a relational postcondition. So, and this pre and post condition is able to talk about the sensor values that are coming from the environment and also the internal state of the reactive system and also the computed output values. But our pre and post conditions are handicapped in contrast to the stateful program logic because our conditions are stateless. So in this circumstance is easy to change. First, we can note that stateful programs require stateful specifications. So what is an easy form to represent the state? Yeah, it is an automata. Here I have shown a simple version of what could be used. We can use an automata in which each state has an associated pair of a precondition and a postcondition. And what we could describe is that if a state in this automata is active, its pre and post condition are applicable for the current execution cycle. So, and if such a relational contract is applied successfully, we can transit to the next state. So, what relation test tables is? A relation test table is a specification language for such an automaton. So this might seem a little bit of cumbersome to have a specification language for such easy automaton, but just for consideration, we have only drawn the edges which are taken on the successful application of a contract, not on the error case where a contract might be failed and how we should proceed with that. So relational test tables describe such an automata. I've already shown that relational test tables are table-shaped specification language which are based on the concrete test tables. So these are the concrete test tables which are used in industry today describes concrete single test cases. So, and our relational test tables are describe families of relational properties between program runs. So, concrete test tables are very popular in industry today because they can be written down by a spreadsheet application. So, just for a brief overview about the syntactical notion of relational test tables. And relational test table is defined over an arbitrary number of program runs. Here in our example, we have the old and the new program run. The columns of the test tables are dedicated to either the program variables of the program runs, so these are the state, the input, the output values, or dedicated to a projection function which can map these program states, the current program states, into a tuple of values. So in the cells of the table, we have the constraints, which are applied on the value of the column and also are applied when the row of the table is active. So in our case, the first row, the CLK projection variable donates that the old CLK is equal to the new clock value. So on the right side of the table, we have the watch column, which helps us to express the number of iterations a row can have or a group of rows can have, depicted by the line with the brackets. So this table states an automata as seen before, as the columns under the assume are our precondition, and the columns under the assert are our postcondition. And each row of a table is a state in the automaton. So a new thing which comes with relation test tables are the control commands. So the control commands takes place in the control column, and besides their assume and assert are constraints on the input values of the underlying program runs. The control commands allows us to manipulate the program flow. So we have identified 3 different commands in our work that are useful for express the relation in evolution scenarios. So, of course, there's the normal execution of underlying program, meaning if I want to say, okay, the program is executed, it makes one activation in a cycle. In contrast, the opposite command is the pauses command. This stops the execution in the current cycle. So the internal program values and the output values of the program run is not changed or not recomputed. So the program one stutters. So this is useful to break off the synchronized loop we have in the earlier slide, where P and Q are executed in every cycle. So with pauses, we can just stop one of the programs from being executed. So, and also we have a reset command, which allows us to reset the state of the underlying program run to an earlier state we've seen before. And as an address to which state we want to insert, we are using the number of a row. So I just want to give a short words on the verification of these tables. So we have implemented the verification pipeline, which takes programs that are written in structured text. This is a common Pascal-like language for the automated production domain. So, and the verification pipeline also takes the relational test tables. So all in all, everything is translated as an input to the new XMV model checker in the SNV format. So, and for the program, we are doing this by symbolic execution. And before the symbolic execution, we are handling the control commands by code augmentation. That means we are translating the program into a form which allows us to manipulate the program flow. So, and relational test tables are done via the automaton we saw earlier that we are encoding into SMB. So, multiple programs ones are very simple to handle with a model checker, as we can just use the approach of product programs inside the model checker. So we also did an evaluation of our specification language to show the feasibility and applicability of the specification and the verification on typical scenarios from the domain of evolution, or the software evolution and information flow. So for this, I want to go into the regression verification, data verification. This describes the possibility that a relational test table is able to capture the relation between two programs and also a functional specification for both programs, side by side in one specification language. So if you consider the evolution of systems, the new revision should normally be equivalent to the old revision. But in some cases, there was an optimization or a bug fix, and in these cases, the behavior should be different. And so we can't compare them to the old revision. So in these cases, we have to give a functional specification to ensure the dependability. So the next thing is, this is also a common case for, at least for automated production systems. These are the typical situation of emergency stops. Emergency stops are very critical in these systems. First, of course, they are an essential safety feature. Second, an emergency stop can occur at any point of time in these systems. So in this scenario we describe, or we want to check that emergency stop is correctly implemented. So, and our specification was that after an emergency stop has happened, the system should behave like a fresh system that are started from its initial state. So this also implies that the system does not store any information that an emergency stop has happened, and so it can be decrease the labor for manual testing the software, because we do not have to consider that multiple emergency stop has happened for the test cases afterwards. So the rest of the case scenarios I want to skip, and just want to give you an overview about the runtimes to close my talk with. So just as a notion, we have used the pick and place unit provided by the Technical University of Munich. This is a community demonstrator for co-evolution in automated production systems. So you see on the right side, the model size, these are taking the complete verification model given in the number of bits in the model checker for the complete product programs. And on the right side, we have the lines of code of all program runs. So, and what you can, what you should notice that the runtime are suitable for a normal engineering task that are ranging from a few seconds up to 2 minutes for the information flow example. All done on a modern laptop computer. So I want to close my talk. The original paper was accepted and presented last week on the Formalized 2020. And the verification pipeline is available as open source. Also, all verification artifacts are available at our homepage. So thank you for your attention.
Okay, thank you very much for your talk. Let me just remind you that you can ask questions on Slido via the link provided. So I would like to ask about delta verification. So what is the output if verification fails?
For data verification is a word we created in contrast to the relational verifications. So data verification means we are verifying the delta between the two software revisions as with a functional specification. So the output would be the counterexample of a functional specification. And as we have embedded both things into an complete verification, into one proof obligation for the model checker, we are getting a counterexample for the model checker, including all program runs and so the usual thing for a safety property.
Okay, thanks. And at some point you mentioned constructing product programs.
Yes.
Are there any interesting challenges that you could mention? I mean, related to your framework?
Yes. Normally, the product programs are very crucial thing to construct for deductive verification. So, but in our domain, these reactive systems are complex in the sense they are huge in lines of code, but they are not huge in complexity of data structure or anything else. These are just Boolean programs, and so we have good results of just using IC3 as the verification engine in the background and just making the normal product programs by sequential composition. So we do not need any interweaving of a product of the programs.
Okay, I see. Okay,